Значит, уважаемые коллеги, начинаем очередное заседание Общероссийского семинара по оптимизации. Сегодня будет доклад Кати Scheinberg из университета Корнелл. Катя является очень известным специалистом, ну, прежде всего, по безградиентным методам. Вот, наверное, многие видели ее книжку, которая лет 10 назад появилась. Вот. Ну и в целом, в общем, в последние годы вот я видел не одну работу. Катя достаточно активно работает в направлении разработки, в том числе адаптивных методов. И надо сказать, что сейчас это в целом достаточно популярно в мире. И вот очень здорово, что у нас эта тема тоже будет представлена в докладе. И вот как раз основная сложность – это адаптивные методы в сочетании со стохастикой. Потому что на данный момент, насколько мне известно, результатов здесь очень мало. И вот сегодня, вероятно, мы что-то такое новое здесь узнаем. Значит, Катя, большое спасибо, что согласились выступить. Пожалуйста, у вас вот, ну, времени столько, сколько потребуется. Ну, обычно где-то часа полтора у нас, так, час-полтора. Хорошо, да.
Спасибо. Я думаю, что я, во-первых, да, меньше времени потрачу, я надеюсь. Ну, если будет обсуждение, только разве что. И это самое. И я перейду на английский в смысле доклада, но я хочу поблагодарить за приглашение. И еще извиниться, что доклад, про доклад мы договорились только неделю назад, и я решила сделать новый доклад на основе как бы обзорной статьи, короткой обзорной статьи, которую мы написали с Фрэнком Кертисом по поводу вот этих методов. И поскольку, когда доклад абсолютно новый, это значит, что там масса будет ошибок и прочих сложностей. Я надеюсь, что не очень много, но по крайней мере, вы первые, кто видит этот доклад. Вот, ладно, начинаем. Okay, so this is based, as I said, this is based on the work with quite a few people because it's based on several papers. Not even all of them are listed here in the first page, but really I'm following a short survey we wrote with Frank Curtis for IEEE journal Signal Processing, I think. And I mean, it's on archive now. It hasn't been published yet, but it will be published soon. Okay, so just to start on kind of a lighter note, so today is actually the 20th birthday of my oldest daughter. And naturally, I was reflecting on 20 years ago in some sense. And 20 years ago, just about a couple of months before she was born, some colleague, I was working at IBM at the time, some colleague came to my office and asked me about how to solve or to help him solve an SVM problem. I haven't seen an SVM problem before. That was, 2000. And I saw that he's trying to solve a convex quadratic optimization problem with first order method. To me, it was horrifying. What? In 2000, you would, of course, think of interior point method as the method of choice. So we had some discussion with him, and we actually tried, and we published a paper on application of interior point methods to these problems. But as we all know, that battle was kind of lost eventually, and now we're looking at a variety of other type of methods. So I just wanted to kind of, as Alexander was saying, put in perspective what has changed in some sense in optimization since 20 years ago. So interior point methods were meant to solve problems fast in terms of complexity, with a lot of iteration costs and very accurately. And now with the fact that, given the new scales of the problems that we are facing, and also the fact that we really don't care if we solve them accurately or not, or sometimes we claim that we want to solve them inaccurately, we are dealing with other type of methods that compute all information inexactly, that deal with some stochastic information. And yet, like with interior point methods, we want to establish complexity guarantees, knowing that they're not going to be very good, or not as good as for interior point methods, but they will, be in general sufficiently good, at least in terms of dependence on the accuracy required, right? So complexity analysis has become kind of front and center in the last decade. What also distinguishes the methods that we are dealing with is that often they're designed for very general problems. They're not designed with any specific structure in mind. And yet structure does play, structure or data specifics play a role. So parameter dependency is a big issue. So for example, choice of a step size is really different for different applications, and often has to be hand-tuned. And so yes, as Alexander said, we're interested in trying to develop adaptive methods. Now, so what are the adaptive methods? I mean, there are different concepts of adaptivity, which I will touch on later as well. But if we're looking at basically optimizing an objective function, then we'll assume it's as smooth as we need, depending on what algorithm we're applying, and generally non-convex, although we'll have some results for convex cases too. So if F is deterministic, the classical approaches to non-convex smooth problems would be line search, trust region, and cubically regularized Newton methods. So basically each of these methods enables us to incorporate some kind of second order curvature information, and also is adaptive in terms of step size, which means that we are trying to have step sizes as large as possible that give us as fast progress as possible. But if we are not successful, we can step back, and we know that, and this is what I'll talk about, if we know that when the step sizes are suitable, we'll make that sufficient progress, and therefore we can analyze the convergence of the method. When F is stochastic, some of these things are much harder to do, and again, we'll touch upon that, but the standard method of choice is various variants of stochastic gradient descent, which is cheap, but per iteration complexity is worse than those of deterministic methods. And then there are other types of problems that are not, so they're maybe stochastic or not, and they have other difficulties. For example, they have noise that not necessarily that can be biased, so you cannot drive it to zero by sampling, or there's no derivative information, and therefore your derivative information has to be obtained by some also types of sampling that may or may not give you unbiased estimators and things like that. Right, so the key thing is, like, can we adapt these methods to the line search, trust region, and regularized Newton to stochastic setting, and can we most importantly analyze it? So I will spend quite a bit of time on the adaptive deterministic framework. This is not, so this is something, this is what we published in this article. We started with analyzing, providing a new type of analysis for deterministic frameworks. Now, they don't need new analysis. The analysis of these frameworks exists in many papers and many books. But to motivate what we're doing with stochastic, we found it easier to explain first the deterministic case. Okay, so let's go over this part. So this is a very generic method that encompasses all three methods, and I'll explain in a minute how. So what are the specifics for the three methods? So first we have basically some initialization step. We choose our parameters. I'll explain what the parameters are. But essentially we have a step size parameter. We have the adaptational, so this is the step size parameter. It's not necessarily the size of the step, it's the step size parameter. It will be specialized in each case. Some measure of progress, and then the control of the step size parameter, how we adapt it, okay? So as any optimization methods essentially would do, we start with, at a given iterate xk, we construct a local model. This model can be a linear model, it can be a quadratic model, can be anything in between, can be other sorts of models as well, but we kind of usually use, you know, we're based on first or second order models of some kind. So then we take a step that is dictated by the step size parameter, and this step is meant to reduce the model, right? So the model tells us in which direction it is good to go and how far, and we're going to do that, and then we expect that some kind of reduction in the model happens. So this is the new value, this is the old value, and the whole thing is sufficiently large, so the reduction happens. And so this is the key thing with the adaptive method. Now, the adaptive method will check if such a reduction or if a matching reduction happened in the function value itself. So we check the function value at the initial point, the function value at the candidate point, and we compare this difference here with this difference here. And so we're hoping that if the model reduced to some reasonable degree, the function will decrease accordingly. All right. And then there are simple two cases, successful iteration, unsuccessful iteration. So successful iteration is when we did achieve the decrease that we wanted, and then we take that step, and then we increase the step size parameter, hoping, unless it's already at some kind of upper bound, this is just a minor thing, but in general, we increase the step size parameter to ensure, or not to ensure, but hoping that maybe we can be more aggressive in the future. Otherwise, we do not take the step and we decrease the parameter. There may be other checks here which are not necessary for deterministic case, will definitely be necessary for stochastic case, and I'll just saying that in general, there can be other conditions for a successful step to take place. Okay, so at this point, let's see if there are any questions about this framework. If not, I'll continue. Okay, so how does it work for a particular method? So this should be in general familiar to most of you. Of course, it's if we have a line search method, then the model is some kind of quadratic model with possibly Hessian approximation, which is positive definite, so we can minimize that model, and the minimum of this model will be achieved here. And we're taking, so it's essentially can be a Newton method if H is exactly the Hessian, but if not, it is something else. If H is identity, this is just gradient descent, and we take a step along that direction, right? Okay, so so the key thing here is where it's a line search, so we're adjusting this step size if we achieve sufficient reduction, and sufficient reduction can be measured, for example, by Armijo condition, which is again a very well-known condition. Not necessarily that condition, can be other conditions, but this is one. Trust region method, you again have a quadratic model with some kind of Hessian. Hessian can be some kind of Hessian approximation. It does no longer have to be positive semi-definite or positive definite. That's the idea of the trust region methods. Then you minimize this model not globally, but because it's non-convex, you minimize it within a ball of the given radius alpha k. So now this step size parameter dictates the radius in which you minimize the model, and the reduction is just measure of the reduction in the function with respect to reduction in the model as a ratio. Okay, so if this ratio is sufficiently large, bigger than 0, then we're happy. Otherwise, we don't take the step. Cubically regularized Newton method is a similar idea, except for instead of minimizing the model in a strictly bounded. Okay, there's a question. But
yeah, hello, Katya. The question is about the cubic method. Is it necessary to bound S, or which can just minimize the cubic model?
I am sorry. You're absolutely right. This is a typo. So there you go. You're absolutely right. Ignore that. I really thought I took it out. It shouldn't be there. It's absolutely should not bound S. Of course, the bounding of S is provided by this term here. And that's the key.
Thank you.
Right. If I put it here, it would not be a cubic regularization method. I'm sorry. I actually thought about removing it, and I assumed I did. Thank you for that. Okay, moving on. So clearly, you're very familiar with the cubic regularized method. So, okay. So we're on the same page. Moving on, and this is just for people who maybe haven't seen these methods very clearly. The successful and unsuccessful iterations essentially come from simply overestimating, in some sense, the Lipschitz constant. So here is example when we take a step that is too large for the curvature. So the curvature goes quickly up compared to the gradient size, and therefore, while we assume that there'll be reduction in the model, there's no reduction in the model. And here is an example when we have reduction in the model, sorry, the reduction in the model and there's no reduction in the function. Here there's reduction both in the model and in the function. So these are the two things that can happen. We're going to see how in stochastic case, much more different things can happen. Okay. All right, so what is the framework for convergent analysis that I want to work with here? So this is a little bit unusual, but it's actually really convenient. So instead of measuring progress in terms of function values only, I'm going to measure the progress of the algorithm in terms of some kind of a Lyapunov function or some potential function, which I call phi. And so this phi k is basically the values of that function at each iteration, and we'll define it individually for different methods. But the idea is that as method progresses, these functions, this phi decreases. Even if we have unsuccessful iterations, the function may not decrease, but the phi will, okay? Then we have these indicators of successful and unsuccessful iterations. We, again, don't really need them here so much, but we use them in the next definition here. We basically say that this indicator tells us what happens with alpha k. So alpha k is the step size parameter that goes up or down by the factor of gamma, whether wk is 1 or -1. I just want to say up front that none of these methods that I'm describing here have to stick to the same gamma being, so you could possibly increase the step size by gamma 1 and decrease it, dividing it by gamma 2 for different gammas, and everything will go through. It's just the analysis gets, you know, somewhat more cumbersome. So I'm sticking to one value of gamma, but it's not necessary. Okay. Finally, this is the kind of the key concept is of stopping time. Simply deterministic case is just the first iterate when we're hitting the appropriate convergence criterion. Okay, so this is an easy thing. You just run until convergence epsilon, and T epsilon is that iteration count. So what we're bounding is T epsilon. All right. Okay, so how do we now perform the analysis? We impose a condition on this whole process. So this process is some kind of iterative process that goes on. We have phi k that goes down, alpha k that goes up and down. These wk's that are indicators for our iterates. And then we have the following, we want the following conditions to hold for our algorithm. We say that this alpha k, while it can go up and down, cannot go below a certain value. It just never goes too small. So there is a lower bound on it, okay, here. So that's the property of an algorithm. We have to establish that it holds for every algorithm, but if it holds, then the next property that we want is that in every iteration, our phi, as I said, decreases. It decreases by some function, fixed function of the step size alpha k times a constant, which is still a fixed function, but yeah. So this is a non-decreasing function of alpha k. So if alpha k is larger, then this value is larger. If it's smaller, this value is smaller. And this is the guaranteed decrease in this thing. And that all happens until we reach convergence. After we reach convergence, we don't care what happens. And we be able to guarantee this. Okay, so if that happens, then let's think about it. This process goes down, starting from phi 0, it decreases. And it cannot possibly decrease further than 0. So in each iteration, it decreases by this much. And alpha k is bounded below. Therefore, on each iteration, it decreases by at least this much. And so the total number of iterations cannot possibly be bigger than this. Okay? Are there any questions about this? This is all generally very simple, but I hope you're following the framework because it's kind of the key logic here. All right. So now I'm going to talk about specifics of the analysis for line search, trust region, and cubic. I mean the regularized Newton, okay? So this is where things get interesting. And again, I'm talking about deterministic, but they're really very similar for stochastic cases. It just, so I'll focus on this for a little bit here. So line search for non-convex case. What is the stopping criterion? It's when the gradient is below epsilon, okay? And what we choose as our Lyapunov function is this kind of thing, which is basically our function reduction. So this is the difference between the function and the lower bound on the function, right? And it's weighed by some parameter. So it's a convex combination essentially of the function reduction and this thing. Now, why is this thing here? You'll see in a second. It's basically kind of a clever way to make sure that this whole thing reduces on every iteration. So then from standard analysis of line search and in general gradient descent kind of a thing. So here I'm just doing kind of gradient descent analysis, but it can be changed if we have a Hessian with a bit of constants. So on successful iterations, if you make a step, you can guarantee the reduction in the function to be of this order. Okay. So these are some constants. This is the constant, which is the Armijo constant. This is some constant that depends on Lipschitz constants and whatnot. This is the step size. And so we guarantee some kind of decrease here. Now this term may increase, but you can see it actually, well, there's a little bit of tiny little derivation that are needed, but eventually can show that the increase of this term is proportional to this term. And so by choosing this value here to be sufficiently close to 0, you can offset and make sure that in its entirety, basically there's a decrease in the function. So phi k decreases, okay? And then when iterations are unsuccessful, you don't move. So the only thing that happens is that alpha k goes down, and therefore you do have a reduction in this whole value because alpha k gets smaller. And so this reduction is here. And basically then you're saying, okay, you have the worst case scenario. There's always a reduction on every iteration. Another question.
Just yeah, sorry. The question is, nu should be sufficiently close to 1, but should be a constant, or it may depend on epsilon, for example.
No, right. That's yeah, exactly. It would not depend on epsilon. So depending how you do this derivation, you may derive it depending on epsilon, and then you will, the complexity would actually not change. You can do this kind of game for deterministic case in different ways, and you can choose the nu differently. For stochastic case, it's very important that it's a constant, but it's a constant, yeah. You can definitely
because it's in the denominator, so it can potentially blow up.
Right. No, it is a constant that it's not even that bad. It's just there are Lipschitz constants in there and things like that.
Okay, thank you.
Yeah, right. But yeah, it's a good point. So in general, one can ask a question, which I did not yet investigate fully, whether we lose a lot in the constants by applying this unified analysis to deterministic cases, because typical deterministic analysis would count unsuccessful and successful iterations separately. And you can definitely do that. And that might be kind of the more efficient way of doing it. And moreover, we can even do it in some stochastic cases, which we've done in some papers. Here, I'm trying to really put one framework on everything. So I might be losing something in terms of constants, but how much I haven't actually yet analyzed fully. So that's so for stochastic analysis, fully stochastic analysis, I don't know how else to do it anyway, but how to do it better. But for deterministic, yeah, we may be losing it with this. But anyway, so it's important question, it's a constant. And then as is evident here when we're applying, so essentially what we're saying is that now with these properties, we are satisfying exactly condition 1 with particular choice of h and some constant here. And therefore, we can apply this result that the bound T of epsilon is, T epsilon is going to be, well, it's going to be this specifically. And yeah, we have to particularize what mu is. In fact, you can find it in the survey. I think we derived the mu very specifically for that. And then, yeah, it's going to be 1 over epsilon squared convergence rate, which is precisely what it is for general line search, non-convex case. All right. Next, trust region. Very similar, different Lyapunov function. Why? Because, so here, instead of alpha k times the gradient squared, we have alpha k squared, because alpha is the actual length of the step, and the guarantee in the function decrease is precisely proportional to alpha k squared, where alpha k is the trust region radius. So basically, on successful iterations, you get this much improvement, and then alpha k increases, so you again just offset the decrease. And here it's much more kind of clear that your mu will essentially just depend on gamma and C2 and eta and nothing else, as far as I can tell. So this would be a nice, you can see that mu is really not a bad constant, and also can be controlled. And then on unsuccessful iterations, you again have simple reduction due to the fact that you reduced your step size. And again, you have exactly the same motivation. So condition 1 works now with a slightly different function of alpha and a different constant. And then again, you have the convergence rate analysis with the same epsilon to the negative, to the power of -2, which is standard. Okay, so this is similar. Finally, the regularized Newton. So those who know the analysis of regularized Newton will basically, as you know, some people here do very well, will know that basically there's slight difference in the way this analysis works. So first of all, the analysis is, the method is designed specifically because it provides a better complexity result. So the final complexity is epsilon to the -3/2. And this is achieved because of the essentially measure of progress in the function. When iterations are successful, are guaranteed to be the, not the square of the gradient, but the 3/2 power of the norm of the gradient at the next step, right? So not at xk, but xk plus 1. So here we put appropriate quantity here. And even though there's xk plus 1 here and xk, it's actually all, you know, works out appropriately. So if we have the decrease, if we have a successful iteration, we have a decrease in the function value of this value, then this item might increase, but we can offset it again by choosing sufficiently small mu. And if we don't take a step, then of course xk and xk plus 1 are the same, so that doesn't change. Alpha k goes down, and therefore we have the decrease overall. And again, we can derive the condition 1 with appropriate function value reduction and the appropriate constant, and we get our convergence rate. Okay. All right. So I hope I convinced you that this works. There are 3 more cases that I can quickly just go over. We can do second order analysis for trust region methods. So that convergence to second order stationary point instead of first order stationary point. Then the measure of, stopping criterion is somewhat different. It's based on the gradient value and the value of the most negative eigenvalue. And then, you design your phi appropriately, and you get the appropriate convergence rates, which is again standard. If you have a convex function and you have line search, you can again apply the same method, but with a differently designed phi k and a different stopping criteria. Now you're converging not in terms of gradient, but in terms of function value to epsilon. And again, you get the same, the convergence rate that is standard. And finally, for strongly convex case here, you have, again, you just slightly different definition of phi k. The measure of progress is now measured in the log of, the proximity to optimality. This is your T epsilon, and the bound is, again, standard. All right. Okay, are there any questions? Okay, so now we're going to move on to the stochastic methods. And we'll basically discuss what differences are and then modify the framework that we're working with accordingly. So what I've written here is the adaptive method as it was before, except for I highlighted in red the slight differences. So if the information is stochastic, what happens is that the local model here, MK, is now random. Right, so if before, you remember for line search and for all these methods, I said that MK was based on basically gradient information and some Hessian approximations. And if we want second order information, Hessians have to be exact. And for regularized Newton, Hessian has to be at least accurate, if not exact, but deterministically accurate. Now it is all random. So the gradient information can be random, Hessian information can be random, and function values can be random. Or they may not be random, but they may be noisy. So the function values are used here, and this is very important. That's one of the reasons adaptive methods are hard, is because you really need to measure progress of your function using possibly incorrect information. Okay. And then you proceed as you do usually, and here I'm just very vaguely emphasizing that you will have to pose in some additional requirement, and that will vary by the method. So the stochastic trust region method will have one type of requirement in addition to standard progress. Line search will have another type of requirement. Line search with not stochastic functions, but noisy functions with bounded noise will have a different type of requirement, and so on. So here you have to be a bit more creative, and that's why you kind of need to apply this framework individually to every method. So what kind of information? So when I say random, the functions, the gradient information is random. The function values may be random. We need some requirements, right? We cannot just say it's random and that's it. So for things like gradient, stochastic gradient descent, the standard requirement is that in expectation you get the true gradient, for example. We both tighten this condition and relax it at the same time. And not just we, I mean, this is what's alternatively been used in the literature. So if you don't bound the variance in any way of your stochastic gradient, the convergence rates are bad. It's kind of a known fact. And if you want the faster convergence rates like the deterministic methods, and if you want adaptivity, it appears that it is necessary in some sense to really control the variance of your estimates. But on the other hand, it is not necessary, it seems, at least not in many cases, to have unbiased estimates. So let me just go over some things that have been used in the literature. So for example, here is one type of requirement. So probability of GK, so GK is now my estimate of the gradient, wherever it comes from. We'll talk in the next slide where they might come from. So GK is some estimate of the gradient. So GK minus the true gradient is bounded by some constant times epsilon, where epsilon is my desired final accuracy. So basically I decide my accuracy ahead of time, and I'm just going to say that I want this much accuracy with the constants have to be something that depends on the method I'm using, but I want this much accuracy out of my gradients. And this in general would work in principle, but it's very, so here I'm calling it non-adaptive, not in the terms of the step size parameter, because you still can apply this sort of setting in an adaptive framework in terms of step size. But what is not adaptive here is the accuracy. When you think about it, if the size of your gradient is really large, then really you don't need to be that accurate, because you can estimate it less accurately and still have useful information in terms of directions of descent. So this is useful for convergence analysis and very easy to use this condition, but it's, you know, it's really not desirable. Now you can use a different condition, such as my accuracy should be proportional to my step size. And here alpha k is the step size, for example, like in trust region, where it's the actual length of the step. And so therefore it's going to be adaptive, because in the beginning of the algorithm, I'm going to be making larger steps because, well, it depends on the variant of the trust region, but in these variants of trust region, the trust region kind of shrinks as you go closer to the solution. So it measures, it stays on par with the size of the gradient. So this is a useful condition that is adaptive and implementable. Here is a different condition that you would use in line search, simply because now your length of the step is no longer alpha k, but it's actually alpha k times gk, because gk is your estimate of the gradient. So you're going along that, and line search tends to take step of this length. So you may want to ensure that your error is bounded in proportion to the length of your step. And here is another condition which is used a lot in the literature and is sometimes completely unimplementable, but sometimes, as I'll tell in a second, is. So this condition is also very nice to use in analysis. It just says that I want my gradient estimate and my true gradient to be close to each other, proportional to the size of the gradient. Right? So the gradient is small, I want it to be accurate. The gradient is large, I don't have to be accurate. And that guarantees, if theta is less than 1, that guarantees that gk is direction of descent. And that makes methods work a lot better. However, it is not clear how to enforce this condition if you don't know the size of the gradient. So in some cases it works, in some cases it doesn't. Now, in terms of function value, so I'm skipping the Hessian information here, because there are, you know, there also works on how accurate Hessian should be, but they're similar to the gradient, so it's not really that, in some sense, they're similar to the gradient. For function values, there, again, conditions can be just make sure that all your function estimates are accurate enough with the given accuracy. You desired accuracy is epsilon, you need function values to be order of epsilon squared, and you just go ahead with that. Alternatively, you can again make it proportional to the current step size, but it has to be squared, step size squared. This comes from simple thinking of these error terms as errors in the Taylor series expansion. So in Taylor series expansion, if you're looking at the radius of size alpha k, then the error in the function and the model can be alpha k squared. Therefore, your tolerance for errors in the function estimate should also be of the same order. Okay, and then similar idea here. This is alpha k squared directly, where alpha k is trust region, the true step size, and then in line search, it's not the true step length. This is the step length, so you use this. And then there are also very nice analysis, much simplified, that you can have if your function errors are bounded with some relatively small error. So that doesn't have to be related to the final, well, it has to be related to the final convergence, but well, yeah, essentially it has to be related to the final convergence. The logic can work here in sort of the opposite direction. You can say, I have a function who has noise and there's nothing I can do about it. So I cannot decrease it. I cannot make it, it's not stochastic, but I have this guarantee. in which case I can design a method and analyze it and show its convergence to some level of accuracy epsilon, this curly epsilon, and there will be a relationship between this epsilon and the convergence epsilon. Okay, and so it also works in the same framework, this kind of analysis. All right. So where do these assumptions come from? Where they, what kind of gradient estimates, for example, can satisfy these assumptions? So one of them, for example, is in non-stochastic setting, but in the setting of black box optimization, where we do not have gradient estimates, and moreover function may be noisy and non-differentiable. There is the Gaussian smoothing way of estimating gradients, which is, you know, fairly well known, I think, by now, probably in this, especially in this audience, and was proposed to, well, it existed, I think, before, but it was analyzed by Nesterov and Spokojny, and we have a paper that analyzed this condition. And so what you can basically show is that for this estimate of the gradient, you actually have this condition without having to know the value of the gradient itself. So that's an interesting case where I mentioned that how somehow condition is really not realizable, but it is for a particular case of function where you measure gradients using this Gaussian smoothing. And so this is one of the conditions we can use. Then the standard condition where you just put some kind of a value here, such as alpha k or whatever, and you want the noise in your gradient to be proportional with alpha k, comes from simply sampling enough in the stochastic gradient setting. So you have stochastic gradient estimates, you sample sufficient number of them, and you reduce your variance to the degree that you want, and then you can have the conditions like these. Because from variance, you can have this concentration inequality, right? Okay, but you also, the nice thing is you can also have these concentration inequalities without having bound on the variance. And that one of the examples, so basically what happens in the presence of outliers. So if you're measuring gradients, but there are some nasty outliers and you want to discount them, then they provide some kind of a bias, but you can compute gradient estimates, the true gradient estimates with high probability quite accurately using not just averages like here, but some other types of averages, which I forgot what they're called, but for example, this paper, this Byzantine robust something estimated gradient estimation has several methods that do that, and it's an interesting application because here it's not very clear what the variance is, but you don't, for our analysis, you don't need the bound on the variance necessarily. There's also Hessian sketching, sparse Hessian recovery, and other methods that again provide similar conditions on the Hessians. All right, are there any questions? Okay, so basically what happens here?
Sorry,
yeah.
sorry, I have a question. Could you open the previous slide? Could you show the previous slide? Yeah.
Yeah.
And am I right that to approximate, to get this concentration type inequalities, you need to have really big n batch sizes in the first and second case, because in that concentration inequalities, you use epsilon, which is small, and
right. So okay, exactly right. So that really pertains to this condition. If I want epsilon here, you're exactly right. N will be large. And that's why this inequality is not a very good one. I don't like these inequalities, and I'm just listing different ones, but instead I would use this one. And I can have analysis with this inequality instead, because I can guarantee or this one, right? And then this one or this one. alpha k is what it is at the moment. And so that doesn't have to be, it's basically should be proportional to the size of the gradient. Now, back to this, it's an interesting point. So if the function is not stochastic, to achieve this concentration inequality from this, n actually has to be order of dimension.
Yeah.
It does not have to grow large.
And do you need to have theta to be smaller than 1?
Yes.
Okay.
Right. Theta has to be smaller than 1. Yeah. So there n cannot be 1 or 2. It has to be something large enough. Right.
But
yes. So in fact, exactly. So you cannot run these methods. None of these methods will work if you don't have sufficient accuracy in the gradient.
And does it make sense to have n bigger than the dimension? Or I mean, to have n comparable with the dimension?
Because why bother, right? Yes.
Yeah, we can approximate the true gradient using these finite differences.
Exactly. Right. That's exactly what we're actually arguing in this paper, that it doesn't seem to make sense.
Okay.
But you're right. So I honestly, yeah, I don't know. We've tried our hardest. So we analyzed the bound here, and we tried very hard to actually show the lower bound on this inequality, right? To show that you really have to sample, because the fact that if you sample sufficiently large number here, you get this inequality, doesn't mean you have to sample this much to get this inequality. From practical point of view, from experiments, you definitely have to. So it seems to be fairly inefficient, but from theoretical point of view, it's still slightly an open question. But we did. Yes, I mean, you're right, exactly. I would do finite differences, to be honest, but for this. But nevertheless, if you do, I mean, people use this, for some reason, this method has become fairly popular lately in things like reinforcement learning. I'm still wondering what is exactly the reason, but I think one of the reasons is when the function here is noisy, then the smoothing kind of works well. Now, finite differences will work well as well if you pick the smoothing parameter correctly. Well, not the smoothing, but the depth correctly. But it's yeah, it's not clear which one is really. It seems to be that finite differences should work just as well. Okay.
Thank
right.
you.
Yes, right. And then, yeah, and here, you're right. You just need to decrease it as you know, as needed. Okay. But in some sense, all these things also tell us, all these results are telling us basically where the variance in our gradient estimates plays a role in convergence rates. So you can view it this way. So, yes.
Sorry, and am I right that for the second case, we need to know the level of our variance, so some estimates in order to
yes.
ensure these assumptions.
Mm-hmm.
Yeah.
Right.
So we consider adaptive methods only in terms of the step sizes. Yeah.
So well, okay. So that's adaptive both in terms of step size and in some sense in terms of batch size. So you can think about it, although it's maybe a little bit harder to really twist analysis this way, but you can think about it as, so let me guess my variance and choose the appropriate sample sizes so that I satisfy these conditions. Sorry. For example, I'm running a trust region method. I have my alpha k, it's given to me, and I want to satisfy this condition. So assuming I think I know my variance, I'm going to run this. And this is all going to work very well until, you know, as long as my, you know, as long as this is satisfied, right? So as soon as I'm not satisfying this, because maybe I underestimated the variance, and so my variance is actually larger, my method is going to stall. So in some sense, I'm going to converge to a neighborhood to some degree. In some sense, I'm going to converge to a neighborhood which is dictated by the size of my errors. So in case when my errors are bounded in the function, I can definitely show that we can do this, right? Without that. I mean, this is something that requires very, very careful, like lining up of various steps of this analysis, which we haven't done yet. But from the philosophical point of view, one can view these results as something that dictates to us where we can converge given our situation, rather than how much we should sample. Okay.
Okay. Thank you.
Yeah, in that sense, it's adaptive. Okay. All right. Okay, so we're done here. Yes, right. So this is just, again, simple illustration of what happens now that we have this whole random information and where the difficulties kind of come in the analysis. So what we had before was the possibility that we had a good step. So the model predicts a decrease, the function is indeed decreases, and also that we detect this decrease because these little red triangles are the actual measures of the function, which are not exactly the function. And if they're accurate enough and the model is accurate enough, then we're happily progressing and the function is decreasing. We may have a situation when the model is completely inaccurate, which we didn't have in the deterministic methods, but so no matter how large the step size would be here, we cannot progress, but because the models are random, we're going to generate these models again, and bad models hopefully don't happen that frequently. And so here in this case, we just simply skip the step erroneously. We should have taken a step, but because the model was so bad, the step is in the wrong direction. So we want to go here, where function will increase. We recognize this factor and we don't move. And then we have two more situations where we actually have a good model, but the estimates are off and they tell us not to take a step that we should have. And so we lose on taking a good step. And then finally, we may take a step which increases the function value because we went in the wrong direction and the estimates were really bad. And so the function value actually increased while we tried to decrease it. So when we're doing this analysis of convergence rates now, when you think about it, things get a bit harder because before we went through the analysis very carefully. We said on successful iterations, our function decreases by a certain amount. On unsuccessful iterations, the step size decreases. So this whole construction of phi was decreasing. Now we don't necessarily have that, okay? But we can possibly have some other guarantees. So here we casting the algorithm as a stochastic process. And the random sequence now phi k has the same meaning and the same purpose. It measures progress of the algorithm. These indicators are random indicators whether iteration is successful or not. Now they're random because they depend on the randomness of the model. So the model may be inaccurate and result in an unsuccessful step. The estimates may be inaccurate, resulting in an unsuccessful step. The alpha k is the sequence of the step sizes, which is also random, and obeys again the same rules, meaning that if the iteration is successful, it's increased, the iteration is unsuccessful, it's decreased. And finally, the stopping time, this time is a random stopping time. It's not a stopping criterion per se, because we don't know the gradient. We cannot stop when the gradient is below epsilon, but it is a stopping time in terms of a stochastic process, meaning that it is measurable by the past history of a stochastic process at time k. Okay? So now we have a stochastic process with a stopping time, and we had this condition 1, which no longer holds. So we're going to modify this condition in the next slide. And here I just want to emphasize what doesn't hold. So reminding condition 1, we said that there was a lower bound on the step size beyond which we would not go. So the step size would never go below that lower bound. Okay. and the reason it was like this is because when the step size was small enough, the iterations was guaranteed to be successful. That's how we did the analysis, basically. In every method, you can show that there's a limit on alpha bar, lower limit, after which the iterations are always successful. It's no longer the case because bad models cause bad unsuccessful iterations, therefore you can never guarantee this. And you cannot guarantee this decrease either on every successful iteration because, again, bad models, they don't give you necessarily this type of decrease, even if iteration is successful, right? So these things break down, but instead, we have the following properties. So here I left some space because I didn't have time to actually draw the picture, but I'll try to draw it. So here's our alpha bar. And before we were saying we would never go below it, but now we might. So our alpha key process can be some kind of a random walk. And then when it hits alpha bar, it can still go below it, but it's still a random walk. And the idea is that once it's below that value, it is, the random walk has an upward drift. That is probability bigger than half of WK being 1. Okay, so what does it mean? It means that once our step size is small enough, while we may not guarantee successful iteration, we guarantee successful iteration with probability at least a half. Okay, which is actually not that strict, not that much. So as long as we're more frequently correct than wrong, essentially, and that means we have an upward drift, and that means that we're going to keep hitting this alpha bar even if we go below it. So our process is going to keep returning to this alpha bar value. And then another condition, so instead of saying that we're guaranteed a decrease in phi k, we're saying that we're guaranteed expected decrease in phi k. So in every iteration, the expected decrease conditioned on the past in our phi process is basically this, the same thing, this h of alpha k. Okay, so we may not guarantee it 100%, but we guarantee it with in expectation. All right. And so then we end up with a stochastic process where it's a little bit more complicated than what is lined up out here, but the essential thing is that you have some kind of a guaranteed expected decrease per iteration. You have a total number of iterations, which is random. You're trying to bound the expected number of iterations, but this process is a super martingale. It's going down in expectation by some guaranteed amount. And then this amount is random, but it's a renewal process. So every so often it is alpha, it's at least as large as alpha bar. Yeah, I'll answer this in a second. It was about the conditions, right? So, so this is basically, so the point is that if we have this condition, then we, through analysis of stochastic process, which is a super martingale with using Bald's identity and, whatever appropriate machinery, we have this. Okay, so the question is, I think, whether this condition is something, it's an assumption or it should be proven. So this is the point, right? I'm saying if I have this assumption, if it works, then I have this result. So next step is to show that this holds, this holds for every algorithm that I want. So I take any algorithm that I want to now analyze. If I am able to show that these conditions hold for this algorithm with the appropriate definition of phi, alpha, and whatever, then I will have this. Okay? Is that clear? So this is essentially, this is the key of where we were working with, like, that's why I went through all this deterministic analysis, saying that we have this general condition, and then for every deterministic method it holds. And so now we have to have this different condition, and we can show that it holds for every particular method we analyze. I will not actually, all these are details. I just kept them just in case there are questions, but here I had the conditions specifically on line search and trust region. So the bottom line is this analysis applies to a stochastic trust region with some small modifications to the standard trust region framework, with again phi k defined kind of very similarly as we did before, with this condition on T epsilon, and with and therefore we have this result. Now I just want to emphasize here that dependence on epsilon is the same as deterministic method. Dependence on Lewis concept is actually the same, and additional dependence is this P. So P is the upward drift of that stochastic process, and that is basically how often our models are good compared to how often they're bad. So if we're if P is close to 1/2, this starts getting close to infinity, and so this complexity is exploding, which is natural. So if you're half the time wrong, half the time correct, then you may not really have a bound on complexity. But when P is reasonably large, then clearly this is a constant, and this is a constant probability. Like you have a constant probability of failure on every iteration, and you still have the bound on expected complexity, which means you converge with probability 1 as well, which is not what the typical analysis of these methods look like. You can have second order results, same thing. You can have a stochastic line search. Stochastic line search is a bit more cumbersome. You can see that our phi k has like an extra term here, which is a control parameter which we need to impose. The conditions are also a little bit harder. There are reasons for that. The dependence on Lipschitz constant is worse, possibly due to just some artifacts of the proof. It may not be a tight constant. And then the same thing extends to convex case with appropriate dependence on epsilon and appropriate change in the Lyapunov function. And then the same thing happens with the strongly convex case and the appropriate dependencies and the appropriate definitions of Lyapunov functions. So, we've done analysis for these. We also have results for cases, somewhat nicer cases, when your functions, when your gradients are random and the Hessians are random, but not the function values. They are, they have deterministic error that they're small. We can analyze and get, like the conditions are somewhat looser in this case, and but the complexity is similar, and the analysis is similar, and you can have. There's other papers now being published trying to use the same analysis for a variety of things. But this is the kind of the most interesting problem in my mind right now that we're trying to work on. So it does not naturally extend, even though we actually thought we extended this analysis at some point to random gradients with parallel parties in our paper. The analysis itself is not correct. And this is a very simple thing, simple reason, is because this object, this is condition for convergence for basically to analyze improvement in regularized Newton, you have to bound the improvement in your step to the size of the gradient and the next step. And this works all fine in deterministic method, but as soon as you are in a stochastic setting, in a general stochastic setting, your next step is not determined at the current iterate. And therefore, this is no longer a stopping time. And therefore, the Wald's equation cannot be applied, at least as it is. And so some other analysis is needed. I'm pretty sure we can extend it. It's just we need to use some slightly different machinery for this. Or we can redefine what convergence means, but that's cheating. Anyway, so that's an interesting open question right now, and I have, some basic conclusions that we think that this framework can be used for a variety of methods, and it's nice because basically it clearly tells you what kind of conditions you need to satisfy, and then you can massage your method to see that it satisfies these conditions in various ways. You can see from these analyses very clearly how the accuracy of the gradient Hessian and the function values progressively get tighter for these methods to work. So for the adaptive methods to work, you need stronger, well, not necessarily just for adaptive methods, but for these methods to work, you need, or for convergence rates to work, you need tighter conditions on the function values than the gradients and than the Hessians. What is very important is where we show convergence with probability 1 and the bound on complexity, even though we have iterations failures. A typical analysis of such methods just assumes everything works on every iteration with high probability, and that's it. We actually allow for the failures to happen and still have the analysis. And yeah, there are definitely more algorithms we can analyze. And here are some of the citations for the papers that this talk is based on. And thank you.
Кате, большое спасибо. Уважаемые коллеги, пожалуйста, вопросы.
Вопросы можно писать в чате, можно поднимать руку в Zoom.
На самом деле вопросов довольно много, просто мы тут с Павлом по ходу доклада много что обсуждали, и как минимум у нас спало много вопросов. Но я думаю, что правильнее было бы дать возможность задать вопросы вот участникам семинара. Вот. А мы, может быть, просто немножко задержимся, и если у Кати будет время, просто еще дополнительно поговорим.
Ну, пока что вопросов нет. Ну вот Павел хочет задать вопрос.
Ну, хорошо, давайте.
Да, спасибо большое за доклад, очень интересно. Вопрос, а есть ли пример, в котором вот эти условия 2 выполняются, пример какого-то метода?
Да, конечно, вот все эти, вот то, что я перечислила, значит, вот, значит, trust region stochastic methods, да, значит, не, ну тут как, значит, они выполняются под определенными условиями на модели, да, то есть, например, вот это вот у нас trust region method, но я здесь, да, я как-то эти слайды не успела поменять, у меня здесь, это, сейчас, одну секунду, это у меня trust region method, да, у меня тут перепутанные альфа и дельта, даже я этот слайд хотела убрать, но решила оставить на всякий случай. Значит, дельта и альфа это одно и то же здесь. Это, значит, условия на, как вот я говорила, условия на градиент. Значит, на градиент модели, которые у нас, ну, estimate, да? Надо на английский перейти, будет проще. Ну, в общем, условия на градиент модели, это, значит, он должен быть пропорциональный trust region radius. И на estimates. Вот. И если эти условия выполнены с определенными вероятностями, и эти вероятности вместе как минимум половина, ну, на эти вероятности еще есть дополнительные какие-то условия свои. В общем, это если выполнены эти вероятности и так далее, то, в общем-то, более-менее стандартный trust region метод выполняет вот эти все условия.
А, например, если взять функцию целевую как сумму каких-то компонентов и в качестве модели брать случайные слагаемые, например, для нее строить модель первого порядка, то есть линейная функция плюс квадратичная регуляризация, то это будет выполняться. Вот эти
это будет выполняться, если достаточная выборка. Значит, достаточная выборка, чтобы вот это вот, как мы говорили, concentration inequality, то, что Эдуард спрашивал. Значит,
то есть,
да, при достаточной выборке.
Батча, достаточно большой.
Да, именно так, да. Это у нас вот описано значит, этот метод описан, сейчас я вернусь к этим самым, значит, в этой статье, у нас описана вот эта вот вся общая фреймворк и конкретный анализ Trust Region Method, и там написано, как, например, выполнить эти условия, да, просто by sampling. Это то же самое, только для line search, и там условия более строгие на некоторые вещи, но то же самое, sampling sufficiently large batch size. Вот это работает, да.
А ускоренные методы можно получить?
Значит, это интересный вопрос. Значит, вот когда, значит, я с ускоренными методами насчет не convex, я перейду на английский, so non-convex accelerated method analysis, I'm not really that familiar with. So for convex cases,
But at least for convex.
yes, so for convex cases, this is interesting. The analysis is, I looked at it, I cannot see how to fit it into this framework. I wish I could see that, because the framework here depends on the expected improvement on every iteration. Whereas the other standard analysis of convex method, not even accelerated, but also accelerated, they have this kind of telescopic behavior, right? That overall you get the improvement, but not necessarily on every iteration. I mean, eventually you do, but it's somehow more, yeah, so I don't see right now how to extend this framework to that. I would love to figure it out. But...
Кстати, есть еще одна сложность. Там довольно часто, вот если брать, во всяком случае, те статьи, что я видел, там используется такая идея, что надо аппроксимировать там градиент, если там безградиентный метод, еще что-то, а аппроксимировать его с достаточной точностью в концепции относительной точности. Об этом есть, например, в книжке Бориса Тодоровича Полика. И там в той же книжке говорится, что градиентный метод от того, что мы вместо градиента будем брать, ну, как бы не точный градиент, но в концепции относительной точности, он не сильно пострадает. А вот что самое интересное, ускоренный метод,
очень сильно страдает.
насколько я знаю, сейчас результатов таких строгих я не видел, но он, во всяком случае, в экспериментах страдает от этого. А что там по теории, насколько он страдает? По-моему, вот как раз Эдуард этим занимался, и довольно сложно, да, такое дело.
Нет, были результаты, там, по-моему, я не помню, но кто-то там у Баха, кто-то там в свое время у них были результаты по этим методам, именно вот показываешь, как надо уменьшать ошибку в градиенте, да, exact gradient, там, accelerated method. У них была статья.
Аспримон? Нет?
А может быть, Аспримон, да.
Я видел его статью, у него не относительная неточность, у него абсолютная неточность. Там довольно симпатичный результат, что абсолютная неточность, она не накапливается, она входит в ответ как радиус на эту неточность, ну, ошибка в градиенте.
Да.
А вот тут речь о другом, о том, что это как бы относительное, это немножко...
Да, я понимаю.
Да. Если относительная неточность есть, и при этом, ну, вот как вот было на слайде у Кати, только, ну, не с, там, грубо говоря, не с вероятностью хотя бы 1/2, ну, скажем, для простоты, даже с вероятностью единица у нас неточный градиент, который имеет относительную неточность, но не стохастический, но имеет относительную неточность, то есть вот эта невязка меньше либо равна некоторой теты, которая меньше единицы, умножить на норму градиента настоящего. Так вот, там, ну, насколько я понимаю, в таком случае с ускорением, ну, во всяком случае, я смотрел это, собственно, как вот с относительной неточностью я смотрел это в применении, применял PEP-техник, ну, вот это Performance Estimation Problem, и там результаты получались, то, что действительно эта ошибка, ну, то есть нельзя брать... грубо говоря, чтобы добиться... Там не получается ускоренной сходимости, если тета получается не слишком маленькой. То есть она накапливаться начинает с какого-то момента. Вот. Ну и, собственно, руками тоже это проанализировать не удавалось. Но вообще, если это говорит ПЕП, ну там, правда, это все было сделано, ну, не то чтобы очень строго, прям.
Эдуард, я не уверен, что многие знают, о чем вы сейчас говорите. Дело в том, что где-то 5 лет назад была статья Тибуля с Дрори, и они предложили общий способ, так сказать, анализа сложности алгоритмов выпуклой оптимизации. И там вот техника, ПЕП ее назвали, она позволяет находить самую плохую функцию для конкретного алгоритма. Для этого надо решать задачу полуопределенного программирования. И это все можно как бы сделать, пакет программ, это Адриан Тейлор это сделал. И можно действительно использовать и просто пытаться под тот или иной метод, скажем, там под ускоренный какой-нибудь метод, смотреть, как вот, в том числе с неточными оракулами, как что работает. Здесь, конечно, много вопросов, связанных с тем, что а вот вы правильный метод берете или нет. Вот конкретно для этого ускоренного метода может она и накапливается, а для другого не накапливается. И уже решать задачу для класса методов с помощью такой техники, это уже не приводит к выпуклой, пускай даже полуопределенного программирования задачам. И это, ну, это отдельная история. Но да, вот как бы для конкретных методов, которые смотрел Эдуард, с помощью такой техники, для которых можно просто действительно найти худшую функцию, на которой вот как бы этот метод хуже всего сходится в рассматриваемом классе. Это сейчас можно делать. Так вот, не получалось.
Ну, я смотрел линейный каплинг только, по-моему.
Ну, это метод Алина Зу, Ареча, да, где-то вот
Да.
лет
Вот.
6-7 назад.
Но, не знаю, я когда разговаривал с Адрианом на эту тему, он тоже говорил, что замечал, что там шум накапливается. Ну, то есть, грубо говоря, статей он, по-моему, тоже не назвал конкретных, где этот вопрос изучался. Но, как я понял, ну, можно еще уточнить, спросить. Я думаю, Адриан Тейлор — это вот правильный человек, у которого это можно спросить, потому что у него, ну, как раз он работает много с performance estimation problem, и вот эти вопросы, у них тоже выходила статья про вот эту относительную, точнее, я могу прислать ссылку попозже, если мне напишите, там вот как раз у Адриана есть статья, с авторами, в которой рассматривается неускоренный метод.
Да, но
И,
это, мне кажется, все-таки это не прямого отношения к тому, что сейчас мы с Катей вот обсуждали, не имеет. Ну да, это на самом деле очень ценно, потому что, пожалуй, вот то, что делал Эдуард, это, в общем, я не знаю, что кто-то еще делал. Хорошо, что сейчас мы это отметили, но, если я правильно понимаю, тут вопрос скорее был в целом, не привязываясь к конкретной технике, то есть есть и другие подходы, как переносить на ускоренные методы. Но вот, если я правильно понимаю, это еще предстоит сделать, вот, если так, да, как бы кратко резюмировать.
Да, да, да. Ну, то есть, да, я просто, я вот здесь конкретного хода не вижу, но это самое, но, возможно, он есть.
Эдуард, есть ли еще вот вопросы, кто руку поднял?
вообще говоря, я не вижу вопросов. Но еще бы я хотел прокомментировать, что вот тут есть связь с Strong Growth Condition, про которую я в прошлый раз рассказывал тоже. Там вот ситуация существенно меняется. Там, казалось бы, похожая ситуация, что там, правда, уже есть несмещенность, но казалось бы, что тоже относительная неточность, но там важно, что это в дисперсии. И вот там как раз с ускорением все хорошо. И, ну, это вот, на мой взгляд, интересный момент, что в ускоренном случае, если у нас уже теряется несмещенность и остается только такое условие относительной неточности, то уже плохо становится. Ну, то есть, по крайней мере, непонятно. Я, по крайней мере, не видел для ускоренных методов с относительной неточностью когда есть bias.
Хорошо, хорошо. Значит, на самом деле есть еще один, по-моему, достаточно важный момент, который, мне кажется, ну, правильно было бы, так сказать, в общем такой дискуссии обсудить. Он связан с тем, что, в принципе, если проследить хронологию работ на тему адаптивных методов, где возникает какая-то дополнительная стохастика, ну, например, в покомпонентных методах или там в методах где стох-оптимизация, то несложно заметить такую тенденцию, что почти все результаты, которые, если удавалось получить, они завязывались на действительно правила типа Армиха или что-то в этом духе, но с некоторым ограничением, связанным с тем, что константа Липшица, градиента, ну или та константа, которая адаптивно подбирается, она подбирается монотонно. Ну, естественно, так сказать, начиная с какого-то заниженного значения, мы начинаем пытаться подобрали какое-то текущее, потом сделали еще сколько-то шагов, оказалось, что надо еще поднять, а вот опустить не получается. Я могу привести какие-то конкретные ссылки, но думаю, сейчас это не очень интересно. Скорее интересно вот мнение Кати относительно того, насколько вот та техника, которая сейчас рассказана, она позволяет уйти в какой степени от вот этого ограничения. Ограничение на самом деле связано со всякими такими empirical процессами. Это вот сложность класса функций монотонных, она намного лучше, она как бы полиномиальная. Сложность класса монотонных функций, в отличие от класса функций, которые могут убывать. Вот. Ну, монотонно возрастать имеется в виду с ограниченным диапазоном. И вот в действительности это достаточно существенный вопрос, потому что, казалось бы, разница между тем, что константа, ну, шаг, если угодно, шаг в градиентном методе может только уменьшаться. Вот такие адаптивные методы со 100 градиентом, они действительно, можно их делать. А вот так, чтобы он мог то повышаться, то понижаться, вот здесь возникает математика, которая, во всяком случае, мне оказывается недоступной. И я не понимаю, как вот это вот вообще в принципе можно сделать, но если что-то можно сделать, то очень интересно как раз понять, как, например, вот с помощью той техники, которая сейчас была рассказана. То есть так, чтобы шаг мог гулять как на увеличение, так и на уменьшение. И при этом была строгая математика.
Ну, не, ну здесь можно, естественно, повышать, понижать, и математика строгая, только проблема в том, что условия гораздо более серьезные то есть надо функцию считать достаточно точно. Потому что в стандартном методе 100 градиента он просто гуляет и не смотрит на то, что происходит с функцией. А здесь эти методы требуют того, что мы очень внимательно смотрели за тем, что происходит с функцией. И на это вот эти условия на оценку функции, они довольно-таки жесткие. Сейчас я пытаюсь...
Ну, а это же как бы речь идет о том, что можно батчить, если я правильно понимаю.
Да, но если батчить, то все это вот здесь именно так. Это вот эти вот методы и line search наш, и trust region, это абсолютно рецепт на то, вот сколько надо батчить, чтобы все это работало. И тогда можно поднимать. Именно в этом вся идея здесь, что можно, пожалуйста, это самое поднять, не можно даже, а нужно. Мало того, потому что здесь как происходит? Значит, здесь немножко другая идея, что мы уменьшаем шаг, если мы считаем, что мы недостаточно прогрессируем. Правильно? Вот. И поскольку мы делаем ошибки, то если мы никогда не будем его увеличивать, то у нас будет все плохо, потому что мы будем продолжать уменьшать, и мы никуда не сойдемся. Вот. И вся идея именно в том, что у нас он и понижается, и повышается, чтобы вот попасть в этот режим, где у меня здесь это нарисовано, вот этого вот стохастического вот чтобы он вел себя вот именно так, как вот здесь на этом слайде, чтобы он, по крайней мере, когда он достиг достаточно нужного уровня, а нужный уровень, понятное дело, определяется локальной константой липшицевой, которую мы не знаем. Поэтому это самое, теоретически этот уровень, он выписывается с глобальной константой. Ну, грубо говоря, да, для градиентного метода просто будет one over Lipschitz constant. Это вот альфа, вот это вот альфа, значит, underscore, да? Это будет просто one over Lipschitz constant. Ну, в более сложных случаях, там, с армихой и так далее, это что-то более сложное. Но вообще вот так вот мы идем туда-сюда, и как только мы попали ниже Lipschitz constant, мы можем случайно еще ее уменьшить, но обязательно должны поднять наверх. Мало того, еще интереснее то, что если мы будем понижать медленно, а увеличивать агрессивно, то у нас на самом деле там вероятность, вот эта вот вероятность не должна быть больше половины, а должна быть больше чего-нибудь, что может быть меньше половины. Например, если мы хотим, чтобы вероятность, то есть, пардон, да, вероятность, нет, да, правильно, если вероятность увеличения, например, 1/10 только, значит, только в 1/10 случае у нас правильный результат, а в остальных случаях неправильный, то мы это можем компенсировать тем, что мы будем увеличивать в 10 раз быстрее, чем, ну, понятно, увеличивать на константу в 10 раз больше, чем уменьшать. И это все равно будет работать.
Хорошо, хорошо. Но это надо действительно аккуратно мне посмотреть. Это как бы такое место довольно неожиданное, потому что действительно это математически обычно вызывает большие сложности. Вот то, чтобы шаг мог гулять туда-обратно. И в основном эта проблема решалась какими-то трюками, вот, которые в Водограде там можно встретить. Вот такого типа. Здесь другая философия. Вот.
Да.
Ну, в общем, да, это...
Да, здесь другая философия, но здесь вкладывается много усилий в то, чтобы посчитать функцию достаточно точно, чтобы не было большого количества ошибок. Мало того, вы можете посмотреть, в этом смысле это интересно, потому что Trust Region Method, как выясняется, он в этом смысле очень хороший, гораздо лучше, чем Line Search. И в этом смысле вот в Водограде, в градиентном, это одна из главных сложностей, возможно, в градиентном методе, который нам пришлось таки действительно серьезно там дополнительные какие-то вводить ограничения и трюки. Но тоже все это работает на полной стохастике, но значит, разница в чем? Что градиент стохастический, теоретически может быть абсолютно произвольно неправильный, в произвольном направлении, произвольного размера. По крайней мере, в нашем анализе. Если мы, да, вдруг увеличим шаг и пойдем в неправильное место, у нас непонятно, что произойдет с функцией. Мы никак не можем ограничить. Вот нам нужно, главное, получить этот результат, что у нас в expectation, да, phi уменьшается. И для этого нам обязательно надо показать, что мы имеем expected decrease. А expected decrease — это значит, что в хороших случаях у нас decrease, в плохих случаях increase, но поскольку там вероятности какие-то имеют соотношения, то это все на самом деле основано на том, что мы определяем, насколько может здесь функция увеличиться, а здесь уменьшиться, и составить их в такое соотношение, чтобы просто выбрать вероятности правильно. Они должны быть константами. Проблема в том, что то есть есть другие, на самом деле, методы, которые делают что-то похожее гораздо более агрессивные, и у них вероятности зависят от эпсилон, и это все гораздо хуже. Но здесь это работает. В Trust Region, что хорошо, что мы далеко уйти не можем. Значит, у нас, какой бы ни был плохой градиент, мы дальше, чем альфа-k, не уйдем, потому что это наш радиус. На следующем шагу, что бы мы там дурацкого не делали, мы, может быть, уйдем на альфа-k в 2 раза больше. И так это не может долго повторяться, потому что, ну, у нас вероятность все-таки ошибок не такая большая, поэтому в конце концов мы сделаем что-нибудь правильное, грубо говоря. Вот. И мы можем балансировать, насколько функция увеличится и насколько она уменьшится на каждом шагу, потому что у нас не очень большой в этом смысле, ну, шаг не очень большой, по сравнению с градиентом, например. А вот в градиентном методе, который Line Search, там можно улететь там куда-то далеко, очень сильно увеличить функцию, непонятно, как это компенсировать. И это вот, наверное, главная проблема в анализе, про которую вы говорите. И нам действительно просто много надо было усилий вложить в том, чтобы вот это ограничить, такие возможности.
Спасибо, спасибо. Может быть, еще возникли вопросы тут по ходу? Эдуард, нет там рук, ничего?
Не, поднятых рук нет. Но я, в общем, сейчас разрешил всем включать микрофоны. В общем, если у кого-то есть вопрос, можете включить микрофон, задать. Можно руку не поднимать. Я пока не вижу вопросов.
Угу.
Ну,
ладно, значит, вроде да, тогда все. Ну да, у нас было около 30 участников, сейчас стало поменьше. Вот, ну, в общем, да. В следующий раз будет доклад Анжели Недич. Мне бы очень хотелось поблагодарить Катю за очень интересный доклад.
Да.
Вот, хорошо пополняющий спектр того, что вот у нас происходит. В общем, на эту тему мы пока не говорили, и кажется, это, безусловно, одна из наиболее таких актуальных и важных сейчас тем, которые вот люди занимаются в оптимизации. Так что здорово, что она у нас была представлена активно работающим ученым, которому принадлежит здесь вот передовые результаты. Это здорово. Вот, так что, наверное, до следующего раза. В следующий раз будет Анжеля Недич делать доклад по распределенной оптимизации. Ну, а, наверное, вот Катю мы бы с Пашей попросили немножко задержаться, если есть возможность, просто отдельно какие-то моменты бы, может быть, обсудили, которые, ну, не всем будет интересно, наверное, слушать, такие технические, ну, буквально ненадолго. Эдуард, может быть, вам тоже будет интересно, я не знаю.
Да. Еще, Катя, не могли бы вы, пожалуйста, прислать слайды презентации? Мы их тоже выложим на сайте Massnet.
Да, я поправлю наши,
Хорошо.
которые уже нашли, да.
Да, и 29-го будет Джордж Лан, он уже подтвердил, он будет рассказывать про обзор, делать про методы, как это называется, ну, Франка Вульфа, значит, как-то, значит,
Да.
conditional gradient, условного градиента,
Условный
наверное, так, да, условного градиента, будет обзор
Да.
Джорджа Лана. Вот. Ну и потом августовская пауза, вот, возвращаемся в сентябре, в августе в Сириусе будет смена,
Да.
там будет много активности
У
оптимизационной.
него как раз недавно препринт вышел по
Да,
методам условного градиента, там, где с линейными ограничениями и с неравенствами, по-моему.
Ну, на
В общем,
Масснете уже значит, анонс есть, то есть можно, в принципе, посмотреть, там, скорее всего, либо уже появилось, либо в ближайшее время появятся анонсы ближайших докладов. Так что до следующего раза.